There's a mountain in Chile where the air barely moves, where rain almost never falls, and where the sky at night is so dark that your eyes can pick out details most of humanity has never seen with the naked eye. At the top of that mountain sits a machine that, for over 2 decades, existed only on paper and budget proposals and the dreams of astronomers who kept insisting it could actually be built. And on June 23rd, 2025, that machine opened its eyes for the first time in public, and what came back stopped astronomers around the world mid-sentence. Not because it was pretty. Telescopes take pretty pictures all the time. It stopped them because of what those pictures actually contained. Millions of galaxies in a single frame, thousands of asteroids nobody had ever catalogued. A level of detail so extreme that a single exposure would need hundreds of television screens just to display it at full size. This is the story of the Vera C. Rubin Observatory, and why the astronomy world is quietly saying the same thing to itself over and over. We were not ready for this. I'm Your Name, and this is Beyond the Stars. If you want to keep up with every discovery this machine is about to make, stay through to the end, because this one is only getting started. Let's set the scene properly, because the location matters almost as much as the hardware. Cerro Pachón sits in the Chilean Andes at an elevation of more than 8,600 feet in one of the driest regions on the entire planet. For decades, astronomers have flocked to this stretch of Chile for one simple reason. The atmosphere here barely interferes with starlight. Low humidity, minimal cloud cover, almost no light pollution for hundreds of miles. It is, quite literally, one of the best windows onto the universe that Earth's surface has to offer. This is also worth noting why a cluster of the world's most important observatories already calls this part of Chile home. But the Rubin Observatory was not designed to just take advantage of clear skies. It was designed to do something no telescope in human history had attempted before. Not to zoom in tighter than anyone else, not to peer further back in time than anyone else, but to watch the entire visible sky over and over every few nights, for 10 straight years, and catch absolutely everything that changes. At the heart of the observatory is the Simonyi Survey Telescope, built around an 8.4-meter primary mirror, more than 27 feet across. That alone would make it a serious instrument. But the mirror isn't even the headline. Bolted to that telescope is a camera unlike anything ever constructed for astronomy. It is roughly the size of a small car. It weighs close to 3 tons. And packed inside it are 3.2 billion individual pixels, making it, without argument, the largest digital camera ever built by our species. To understand what that number actually means, consider this. A single photograph from this camera, printed at full resolution, would require something like 400 large, high-definition television screens just to display it properly. One photograph, 400 screens, and this camera isn't taking one photograph a year, or one a month. It is designed to take a new 30-second exposure roughly every 40 seconds, all night, every clear night, scanning across the entire visible southern sky once every 3 days. When the first images were finally released to the public in June of 2025, after months of quiet testing behind the scenes, the observatory team unveiled 2 showcase pieces that immediately made headlines across the scientific world. The first was a sweeping view stitched together from over 1,000 individual exposures, showing the Virgo Cluster, one of the nearest large collections of galaxies to our own Milky Way. Inside that single mosaic sat roughly 10 million galaxies, spirals caught mid-rotation, ellipticals glowing softly in ancient light, pairs of galaxies locked in slow gravitational collisions that have been unfolding for hundreds of millions of years. And here is the detail that actually made astronomers go quiet for a moment. Those 10 million galaxies represented barely a rounding error of what this telescope is ultimately built to capture. Over its full 10-year mission, the Rubin Observatory is expected to image roughly 20 billion galaxies. The very first release, the one considered a triumph on its own, accounted for something like a 20th of 1% of that total. The second image released that day pointed the camera, somewhere closer to home, toward 2 glowing clouds of gas and dust known as the Lagoon Nebula and the Trifid Nebula, both several thousand light years from Earth, both places where new stars are actively being born out of collapsing clouds of hydrogen. Astronomers have photographed these nebulae plenty of times before, but almost always through a narrow, zoomed-in lens designed to capture fine detail in a small patch of sky. Rubin did something different. Because of its extraordinarily wide field of view, capable of capturing a patch of sky roughly 40 times the size of the full moon in a single exposure, the observatory didn't just photograph the nebulae up close, it photographed the neighborhood around them. Star clusters, background galaxies, faint structures normally invisible in a standard shot, all sitting in frame at the same time, at a scale that made the nebulae themselves look almost small by comparison. It's the difference between a photograph of a single tree and a photograph of the entire forest that tree happens to be standing in, with every leaf still sharp enough to count. Here's where this stops being just a story about pretty pictures and starts being a story about what those pictures are for. The Rubin Observatory was never really built to be a camera in the traditional sense. It was built to be a detector of change. Every 3 nights, it completes a full sweep of the visible southern sky, and every time it does, it compares what it sees against everything it has recorded before. A star that suddenly brightens, an object that has shifted position against the background stars, a galaxy that flares with new light where there was nothing the night before. All of it gets flagged automatically in close to real time and sent out to astronomers around the planet so they can point other instruments at the event before it fades. In its very first 10 hours of test observations, before the mission had even officially begun, the observatory detected more than 2,100 previously unknown asteroids, 7 of which were classified as near-Earth objects. For context, the entire combined network of ground-based observatories on this planet typically finds around 20,000 new asteroids in an entire year. Rubin found a tenth of that number in less than half a day of testing. That single fact points toward one of the observatory's most consequential jobs, planetary defense. Every year, small and mid-sized asteroids pass uncomfortably close to Earth, most of them undetected until they are already nearby, simply because no instrument existed with the combination of speed, sensitivity, and field of view needed to catch them early. Rubin changes that equation entirely. Scientists expect the observatory to eventually catalog the vast majority of large near-Earth asteroids that could pose any meaningful risk to our planet, tracking their orbits years or even decades in advance, giving humanity something it has never really had before. Advance warning, measured not in days, but in a comfortable cushion of time. But asteroids are really just the most immediately dramatic part of a much longer list. The Rubin Observatory has 4 primary scientific missions written into its charter, and asteroid detection is only one of them. A second is the search for evidence of dark matter and dark energy, the mysterious substances that together are believed to make up roughly 95% of everything in the universe, despite the fact that no instrument has ever directly detected either one. By tracking how billions of galaxies are distributed and how they subtly warp the light passing near them, Rubin's data may offer astronomers their best opportunity yet to map the invisible scaffolding holding the cosmos together. A third mission focuses on transient events, the flickers and explosions that light up briefly and then vanish. Supernovae, gamma-ray bursts, sudden flares from black holes tearing apart unlucky stars that wandered too close. Because Rubin rescans the sky so frequently, it is expected to catch thousands of these events in progress, often within hours of them beginning, instead of discovering them days or weeks later once the most interesting part is already over. And the fourth mission focuses closer to home on mapping the actual structure of our own Milky Way galaxy, using ancient pulsating stars called RR Lyrae variables as measuring sticks to chart the galaxy's outer halo in 3 dimensions for the first time. Now, here's a detail that tends to surprise people who assume space telescopes are automatically better than anything sitting on the ground. Hubble and the James Webb Space Telescope were launched into orbit specifically to escape Earth's atmosphere, because even in the clearest conditions, our air distorts and blurs incoming starlight just enough to limit what a ground-based telescope can resolve. That has been true for as long as ground-based astronomy has existed. And yet, sitting on the surface of the planet, breathing the same thin, dry air as everyone else on that mountain, Rubin is producing images that rival, and in terms of sheer coverage, genuinely surpass what space telescopes can achieve. Not because it beats the laws of atmospheric physics, it doesn't, but because its mission was never about achieving the tightest possible zoom on a single distant galaxy. It was about seeing an enormous amount of sky all at once, over and over, faster than anything else humanity has ever pointed at the stars. Hubble can show you the fine detail on a single house. Rubin shows you the entire city, every building included, updated every few nights. None of this comes without a cost, and that cost is data, an almost unimaginable amount of it. On a typical night of operation, the Rubin Observatory generates roughly 20 terabytes of raw imaging data. To move that data off the mountain and into the hands of scientists fast enough to be useful, engineers built a dedicated high-speed fiber connection running from the observatory in Chile directly to processing centers in the United States, capable of transmitting data at roughly 100 gigabits per second. Once it arrives, an automated pipeline gets to work immediately, calibrating each exposure, aligning it against previous scans, flagging anything that has moved or changed brightness, and folding the results into a constantly updating digital record of the sky. By the time the 10-year survey concludes, the observatory is projected to have gathered something in the neighborhood of 500 petabytes of data, cataloging tens of billions of individual celestial objects. It is less a photo album at that point and more a living, continuously updated model of the observable universe, one that professional astronomers and, through public tools built around the data, ordinary space enthusiasts will be exploring and mining for new discoveries for decades after the observatory itself eventually goes quiet. There's one more thread worth pulling on, because it connects directly to something that has captured public imagination in recent years. Interstellar objects, visitors from other star systems passing briefly through our own. Only a handful have ever been confirmed. Oumuamua in 2017, discovered almost by accident and gone again within weeks. Borisov in 2019, spotted with barely enough time for serious study before it faded from view. A third, catalogued as 3I Atlas, was identified in the summer of 2025 by a separate Chile-based survey system built specifically to watch for exactly this kind of object. Each of these discoveries shared the same frustrating limitation. By the time anyone noticed them, they were already halfway through their brief visit to our neighborhood, leaving scientists scrambling to gather what little data they could before the object slipped back out into deep space, never to be seen again. Rubin's combination of wide field of view and rapid repeated scanning gives astronomers something they have never really had with these objects before: lead time. The possibility of catching an interstellar visitor while it is still far out, faint and slow-moving, long before it makes its closest approach to the sun, giving researchers weeks or months to study something that used to disappear in days. Step back from all the individual numbers for a second, because the real story here isn't any single statistic. It's the shift in how astronomy itself is now being conducted. For most of the history of this science, discovery meant pointing an instrument at one object, one patch of sky, and studying it in isolation, then moving on to the next target on the list. Rubin doesn't work that way. It doesn't choose a target and stare at it. It watches everything, continuously, and lets the universe tell it what's interesting. A star that flares, a galaxy that shifts, an object that moves against the fixed background of the sky. The observatory finds it, flags it, and hands it off to the wider scientific community, often within minutes of it happening. That is a genuinely different way of doing astronomy than anything that came before it, and it is why so many researchers, when asked to describe what these first images actually mean, keep circling back to the same word. Not beautiful, not impressive, transformative. The Vera C. Rubin Observatory is named after an American astronomer whose own work decades ago provided some of the first solid evidence that dark matter exists at all, evidence that the scientific establishment of her time was initially reluctant to accept. There is something fitting about the fact that the instrument bearing her name may end up doing more than any other single telescope in history to fully pin down what that invisible substance actually is. It has barely begun its 10-year mission. The images released so far represent a sliver, a preview, a proof of concept for what is coming over the next decade. Millions of new asteroids, thousands of supernovae caught in the act, a three-dimensional map of our own galaxy more detailed than anything that has ever existed. Possibly, if the timing lines up, a close and early look at the next visitor from another star system before it disappears back into the dark it came from. We are, in a very real sense, at the opening minutes of a 10-year film about the universe, and the Rubin Observatory just handed us the trailer. If the first 10 hours of test observations could rewrite how fast we find asteroids and hint at millions of galaxies we've never seen, it's worth asking what year 5 or year 8 of this survey is going to look like. Make sure you're subscribed and notifications are on, because every time this observatory catches something new, a flaring star, an unexpected asteroid, a visitor from another solar system, we'll be here breaking down exactly what it means.